Hello! This is an overview of the Cinemagraph Generator that Garrett and I have been working on together. We decided our goal was to make a seamless video loop from a handheld video taken by the general public. This can be thought of as almost a magic picture, like the moving images within newspapers in Harry Potter. A picture of this format can be used for many different applications, including sharing moments or scenes online, creating beautiful looping GIFs of real-life scenes, and even creating custom videos of desktop backgrounds. This type of pleasing moving picture is often called a cinemagraph, which is usually seen in the form of a GIF that has a scene with subtle motion in it. For our research, we used a tool called Jupyter, which combines the power of interactive Python with HTML and JavaScript in what it calls notebooks. Notebooks are typically edited in the browser with a standalone web server that Jupyter provides. In our work, we used Visual Studio Code to edit our notebooks instead of the web server. VS Code has Jupyter integration built in by default and comes with some handy features that aren't available in the browser, like debugging and memory inspection. Inside our notebooks, the primary library for our work has been the fantastic OpenCV library. For our process, finding good start and stop points to create a loop is crucial. In order to make it feel seamless and avoid a jarring sensation, the beginning frame and end frame should look very similar to each other. To visualize the similarity between pairs of points through the video, we created a similarity matrix where we compared every part of the video to every other part. One huge takeaway we've learned from this project is that finding ways to visualize the process of what's happening can be extremely helpful for understanding how our code is running and for finding bugs. In order to get the error between two arbitrary frames, we simply subtract the two frames from one another. Here's a visualization of that subtraction. To get the overall error between these two frames, we take the absolute value of the differences and sum them together. To visualize the similarity within the entire video, we take this summation and put it into this graph. Now we repeat this process for every possible pair of frames within this matrix, or until we have enough of a picture of what's going on. Picking a good place to splice the video becomes a task of finding a spot that is darker than the rest. We also need to avoid the diagonal, because this area would give too short of a clip. However, when we tried this, it still ended up producing unsatisfactory results for videos taken without a tripod. This is because even slight rotations of the camera can make very noticeable offsets that give a jolting look when the video loops. However, we realized that aligning the frames to each other can fix this and significantly reduce the error. To do this, we took one frame and compared it to another, but with different up, down, and side-to-side offsets. We can also plot the error of these different possible offsets in another matrix. As we can see, moving the frame up reduces the error quite a bit. To best align one frame to the other, we need to find the darkest spot in this picture. This is a classic problem of finding the minimum. This got us searching and learning about gradient descent and other similar techniques to be able to find this minimum quickly and robustly. Using the slope of this field allows for gradient descent. To find the slope at some particular offset, we take the frames, convert to black and white, slightly blur the frames to provide a more stable slope, then apply the desired offset to the second frame. Then we take the difference of these two frames using subtraction, apply both an x and y derivative kernels to the first frame, and finally multiply these with the difference of the two frames. This gives what I call correction pictures, where positive values mean positive movement will reduce the error, which means they're better aligned. We sum up all of these values in the x and y corrections to get the overall slope for each one. Now we can use this slope to know which direction to go towards the minimum, and can iteratively move towards it. We ended up making an ad hoc iterative algorithm using both gradient descent and slope extrapolation, as well as starting with low resolution frames and moving to high resolution as it goes to quickly find the minimum. Here's what it looks like after the alignment. If we again make a similarity matrix, but align each pair of frames before finding their error, this is the result. As you can see, the image is now much darker overall, which means the error has been reduced in general. After some investigation, we found that parallax is now the main cause of error. We can also see some new patterns emerge. These dark streaks of low error correspond to moments in the video where the camera was in the same spot, just at a different time. This meant little parallax and thus low error. Now, fixing parallax for the whole video is a much harder task, so we'll just leave it to the responsibility of the person taking the video for now. If they want a better result, they will need to use a tripod. To make the splice even more hidden, we use a crossfade during the transition. To complement this, instead of finding a point of low error, we can find a diagonal line, which will mean low error during the whole crossfade duration. For this specific video, this top diagonal was caused by the camera not only being in the same place, but also moving in the same direction for a short period. If we use this location for the splice and put this all together, this is the result. Thank you.